Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're happy to have Shankar Pamidi here. He's up here for most of the week,
right.
Yes? And I'm really interested in this because I got a note from him, I don't know, a month ago or so, saying I can redo lots and lots of different projects that you've worked on in a unified way. So I'm really looking forward to hearing this. He has universal techniques for preferential attachment, and he'll talk about local and global analysis.
Okay. Thank you. Okay, so essentially this, the story behind this talk is I went to this IPAM conference in May, and then there were some very interesting talks on preferential attachment. And so one of the speakers, Noam Berger, who's like a very good speaker and also a collaborator of yours, he was mentioning in his talk, and also later he was telling me how in some sense there are these various random network models, and a lot of work has been done in trying to derive asymptotic degree distributions and things of that sort. But there hasn't been, it's somehow difficult to understand what is a complete picture of the local neighborhood around nodes, or more global characteristics like the height, the diameter of these networks, the maximal degree, and so on. So I started thinking about these around 2 or 3 months ago, and using some abstract math, not necessarily very difficult, you can understand a lot about these networks. So what is the basic motivation? So in the recent past, there have been a lot of models on preferential attachment to model various real-world networks like the internet, web pages, and so on. And one of the most popular models is preferential attachment, various schemes of preferential attachment. And there are hundreds, if not thousands, of papers in a very large number of fields: systems biology, computer science, statistical physics, trying to explain various real-world networks using these preferential attachment schemes. And they seem to come up in places where somehow you wouldn't expect them to come up. Jennifer and Christian have worked on this competition induced preferential attachment, where in the beginning there doesn't seem to be any pure preferential attachment scheme, but using very nice arguments they actually showed that it's equivalent to a purely preferential attachment type scheme with some attractiveness function. So now what is the in the 2 or 3 months that I've spent looking at the literature in the mathematical world, so for many of the models there's been an enormous amount of work on the degree distribution, the asymptotic degree distribution, and there are lots of subtle methods using, essentially to my knowledge, using recursions and concentration inequalities, earned models, and so on. And many of the methods are very subtle, so very difficult. But as Noam told me, it was difficult to understand what is the actual neighborhood around a random node and various other questions, more global characteristics. And somehow these questions are very important because to understand, say, mixing time of random walks or the spread of epidemics on these networks, and also something I'll talk about today, so the spectra of the adjacency matrix for these trees and networks. It's important to understand more locally what happens, a much better local picture, and as well as this maximal degree and so on. So I started thinking about what is the central math theory which can solve a large number of problems. Okay, so the basic aim of this talk is to derive a universal method which somehow seems to work in a large number of interesting cases and gives a lot of information. And so we'll largely deal with trees, which is many of the more advanced preferential attachment models seem to start off with trees, but they also give very nice results for these preferential attachment models for growing networks. So for a particular class of networks, they tell you what the maximal degree would be and also the degree distribution. And they're somehow, at least I think it would be difficult to derive these using any other techniques. Okay, so a very quick outline. So I'll tell you what the model is, what the general scheme of attachment is, and then I'll tell you some examples which are of current interest. Then I'll just give you a sample of global results. So the thing is, these methods somehow give you almost one or two line arguments, what the root degree should be, what the maximal degree, what the height is, in percolation, what is the size of the component attached to the root, and things of that sort. So I'll tell you how you can do this very quickly. Then I'll tell you a bit about structure theory. So I'll describe the construction of infinite trees. So these are somehow trees with only one end. They're called single infinite trees. So they have just one end going off to infinity. And how, and how using these infinite trees you can get a lot of information about the degree distribution. So this is of course what people have been doing a lot. And also other things such as the random adjacency matrices and spectra. And then I'll tell you how these methods also apply to random networks. And there's not going to be much time to actually talk about fitness models. And then I'll tell you some open problems. So these are more, half-baked open problems which even I don't think make much sense. And the idea is perhaps you can tell me more interesting problems to work on in this area.
Maybe the semester will end before we get
Right, yeah, that is also possible. Okay, so I have a weird way of, my talks are slightly weird in the sense my conclusion comes after my introduction, so there's no actual conclusion. So the conclusion comes now, so before people start running away. So the basic take-home messages are, this method seems to work in a number of models. So there's been a tremendous interest in these power law distributions in the recent past, and there are two sophisticated reasons why these power laws arise in various systems. One is systems at criticality, like the integer lattice at criticality, the size of the clusters and so on. Power laws arise there. So systems at criticality is one place where power laws arise. And another sophisticated reason for the arisal of power laws is two competing exponential, not distributions, but two systems where one system is growing at an exponential rate, and you observe this system for a different exponential amount of time. So it grows at an exponential alpha rate, and you observe the system for an exponential t beta amount of time. So this is slightly vague, but as I get to the talk, you'll see what I mean. So preferential attachment in some sense seems to belong to the second class of models, why this power law arises. And once the basic idea of embedding these into something called continuous time branching processes, then somehow the results come out very easily using the stochastic process approach. Okay, so let's get started. So what is the basic scheme? At time 1 you start with a single node. So this is, first I'll tell you how you grow trees. So these trees have a distinguished root, which is the first vertex to start the entire scheme. So at time 1 you start with a single node, and suppose you've constructed your tree at time n, a new node comes in. So firstly at this time you have, for each vertex in your tree, you have a function. So this function tells you how attractive is this particular node for the next node to come in and attach itself. So you have a function on the vertex set of your tree. Node n plus 1 comes in and it attaches itself to one of the nodes in your present tree with probability proportional to this attractiveness function. So this is the basic scheme. And most of the examples that I'll consider, you think of this function as essentially a function of the degree, or since these are rooted trees, you can think of these trees as directed away from the root. So as functions of the out degree at time n. So most of the functions that I'll look at look like this. So this is an example. Node 1 comes in, node 1 starts the entire process, and then node 2 comes in, attaches itself to node 1. Node 3 comes in, attaches itself to node 1, 4, 5, 6 attach themselves to 2, and so on. So this is how the tree grows, one by one, attaching itself with probability proportional to this particular attractiveness function, f.
So what is the function allowed to depend on?
Right, no, I'm not going to talk about, so this is the general setup, but I'm just dealing with just particular examples. So in some cases you can't exactly define a proper scheme in the sense that the continuous time branching process explodes in finite time. So these methods then don't work. But I'll just talk about the particular models where they seem to work well. So some of the particular cases is the usual, so this Yule, Simon, Barabasi, Albert model, or just the Barabasi, Albert model, where this f of k is k plus 1, the total degree, or the out degree plus 1. And then if you just perturb it a little, you have the linear preferential attachment model, k plus 1 plus a, and surprisingly, although you wouldn't expect, this somehow changes everything to a large extent, like the maximal degree, the size of the percolation component, and things of that sort. And then you have these random fitness models, which are analyzed by Jennifer, Christian, Sebastian over here. So you have, what do you do? So each node, when it's born, it also gets a random fitness with some distribution mu. So that is how attractive it is, and this fitness remains constant. And the attractiveness function at any time is proportional to the degree of the node, or the out degree of the node plus 1, times this fitness of the node. So this, and there are variants where you have additive fitness instead of multiplicative fitness, and then there's the sublinear preferential attachment, and then there's this competition induced preferential attachment, which is somehow there's a Markov description. So I'll tell you what the Markov description is once I come to how you analyze it. And then there are attachment networks, so not necessarily trees. So trees are good, but then attachment networks are sometimes more realistic. So how are these attachment networks constructed? So at time k, a node k comes in with wk edges. So the usual way you assume is wk is just some m, let's say 10 edges. Each new node comes in with 10 edges and then attaches itself to the network. But you can in general assume that it has some distribution, and if you do so, you get very nice results, or somehow non-trivial results. So how do these edges attach themselves to the network? So each edge attaches itself to the network. So a node comes in with k edges. It takes its first edge, attaches itself with probability proportional to the present degree. All the degrees are updated, and then the second edge is attached to the network, and so on. So one by one, you keep recursively attaching each edge until your network is formed. So you can think of attachment networks as well.
What about this more general attachment networks analyzed by Cooper and Frieze? Do they fit or not?
Well, I think they do, but I've not looked at it. So I kind of got exhausted after analyzing these models, and I haven't looked at this. So this is, as you said, so this is one particular case of their general attachment scheme. So, okay. So I think they do fit if you tweak some parameters and tweak the attractiveness function, but I'm not sure. Okay, so you're given an attractiveness function. Now I'll tell you a continuous time construction, which is somehow at the very basis of all the analysis. So keep in mind that right now you have an attractiveness function, one of these f's, or an f that you've constructed. So given an f, first, so there are two things. First, what you do is you construct a Markov birth process. So what is this process? It's just you start with one individual at time 0, and this individual keeps reproducing people. So it is not a branching process yet. Just this one individual keeps producing children. So how does he produce children? Suppose by some time t he has k children, then the chance that he produces an individual in the next small interval is basically proportional to this attractiveness function f of k dt. So he produces at rate this attractiveness function, so f of k times dt. So this is the rate at which he reproduces children. So this is no branching process, just the rate at which a person reproduces new children.
So it's more like Yule or an
Very good.
model.
Right.
I mean, this is a continuous time.
Right, exactly. So, exactly. So we get the Yule process. If for the usual preferential attachment, you get the Yule process. Now you're given an attractiveness function, then you construct this point process of reproducing children, and after this you can construct a continuous time branching process. So how is this constructed? You start with a single node at time 0, and it gives birth to children at these times of this point process, and each node which is born, it has its own independent copy of this point process. So this is a random point process, so it has its own independent copy, and it reproduces at these times, and so on. So you continue doing this. So anyway, so this is just a picture. You start at time 0. This person produces children at these times, so you think of time going upwards. This person produces children at these times, and each of these have their own point processes, independent, and keep reproducing their own children. So you have the attractiveness function, you go to a point process, and from there you go to a continuous time branching process. So the key connection is the following. So suppose you just sample this branching process at times where the size of the population is equal to n. So assuming that you can construct this process, and suppose you just sample this at times when the size is equal to n, then the tree that you get has the same distribution as the random tree with attractiveness function f. So that's the key, that has been observed, and these kind of ideas have been implicitly used. Even in Jennifer's and Christian's analysis of this competition induced preferential attachment, they did use continuous time, basically this idea to get the degree distribution. So I'll just tell you the basics of branching process theory, which is needed. So this, somehow this was conjectured as far back as Euler. Essentially the stable age distribution was conjectured by Euler, and it was developed by Jaggers and Nerman. Swedish probabilists in the 1980s. And I guess one of the main reasons why this still hasn't come into the, or hasn't been used here, is because the papers are remarkably difficult to read. So, I still don't understand, after trying to read them 10, 15 times, I still don't understand more than 2%. But anyway, so what is the basics that you need? So these processes, the way I told you, these processes grow at an exponential, grow exponentially if you can construct them. So what that means is by time t, they're approximately the size of the population is e to the lambda t. What is this lambda? So this lambda, when you're doing this recursion method of proving preferential attachment, it comes up quite often. So this, in this context, it's a very important characteristic. It's called the Malthusian rate of growth. So it has a name. And given my entire story, how do you actually compute it? So you look at the point process, you look at an independent exponential random variable, and you ask, what is the expected number of children that a person has by time t lambda if he's reproducing using this point process? So you solve that you solve this equation. So let this be equal to 1. So this is lambda that you need for a particular model. This lambda tells you this is the Malthusian rate of growth for your process. Okay, so what are the more exact results? So if you assume a slight technical condition, then basically you have that the size of your population divided by e to the lambda t, this converges almost surely to some positive random variable.
But, I mean, you say it's technical, but isn't that condition violated in, like...
No. So the thing is this condition basically says that your degree distribution has first moment times log plus...
Right, so 1 plus that.
This is the
Right.
statistical
fine.
condition.
Right, it's a second, yeah, exactly.
Is it known to be if and only?
Yeah, in most cases.
Right.
Right, good.
Right. So but the point is that in all the models that you or many of the models you analyze, it somehow is satisfied. Anyway, so the important point to note is, you have this. So the time for you to construct your the time for you to construct your tree on n vertices, Tn. This is basically because of this basic fact. It tells you that the amount of time you have to wait before you can construct your tree on n vertices is approximately 1 by lambda log n plus or minus some probabilistic some term which is bounded in probability. So it gives you very sharp results as to how much time you have to wait before you can construct your tree on n vertices. So these results are either implicitly or explicitly known in various places. Yeah, sure.
The second asymptotic, the one we have on the bottom in red, doesn't require the Keston statement.
Well, but if w is equal to 0, then somehow, things could get messed up.
Much further when you pass the log.
Right. You're right. But, in most of the cases it's satisfied, so. No, very good point. So how do you use these results? So, you have these results, so how do you put them together to get information? So this is actually global information about your trees. So you want to know what's the maximal degree, what's the height, and so on. So let's just study one example. So suppose you look at the most popular preferential attachment right now. So this Barabasi-Albert or Yule, Simon, Barabasi-Albert model, where f of k is equal to k plus 1. It turns out that the offspring distribution in this model is the Yule process, as Jennifer said. You can compute what the Malthusian rate of growth is. So here lambda is equal to 2. Okay, so now what do you do? So the degree of the root is the number of children that the root reproduces by the time you stop your process. So the number of children that the root reproduces, this point process for the root, up to time tn, the time for you to construct your tree. So how can you use this? So what I told you in the previous slide is the amount of time required is half log n plus or minus this quantity. Okay. Okay. So what does this imply? So this point process, which I told you is the Yule process, also grows explosively. So it's known, various very good results for the Yule process are known. So in particular, it's known that the number of children that a person reproduces by time t is e to the t. So what does this tell you? The degree of the root, this is the number of children that the root reproduces by half log n plus or minus some term. So this is basically by this fact, e to the t, e to the half log n. So it's of order square root n. So you get almost immediately you get what the size of the maximal, sorry, not the maximal, the root degree should be. And if you analyze a bit more, what the entire story tells you, then you get that the degree of the root divided by square root n, this converges to some random variable. So this is an actual random variable. It's not degenerate, and it's strictly positive. So z is greater than 0. And you can also get an explicit recursive construction. Okay, so root degree is good, but you can get even more. So you can find out what the maximal degree is as well. So I won't tell you the full details as to what happens, but so I told you, you have these nodes coming in quicker and quicker. So by this natural time scale, I mean this exponential rate of growth of this process. So because of this, somehow the basic heuristic is the maximal degree in most cases has the same order as the root degree. So essentially the maximal degree occurs in a finite neighborhood of the root. And it's 1 or 2 pages, but essentially large deviation type arguments, not at all complicated. You can get results of the following. So if given any epsilon, I can find a constant k epsilon such that the probability that the maximum degree divided by square root n, the chance that the maximal degree is of size greater than k epsilon times square root n is less than epsilon for large n. So you can get these type of results. And for this particular case, so this part has also been analyzed by Mori in a set of papers, but using completely martingale type arguments. What you can also show is that this maximal degree divided by square root n converges in distribution to some random variable. So there's a distributional convergence for the maximal degree as well. And okay, so this is somehow known results, but just using this entire technology, somehow you get non-trivial limiting results. So if you look at the preferential attachment model with sublinear preferential attachment, and you ask what is the size of the root degree, then it scales as log n raised to the power 1 by 1 minus alpha. So alpha is less than 1. And this converges in probability to some constant. So this theta alpha is the corresponding Malthusian rate of growth. And you get exactly what it converges to. So this is just quickly a lot of formulas, etc. But the point is, so these ones somehow I didn't find in the literature, so I'm assuming they're new. But these ones presumably, the first two presumably they've been known in some form or the other. But for most of the models, for most of these models, you can compute what the root degree, the order of the root degree is, and also the order of the root degree and the maximal degree is the same. And okay, so this basically tells you, does the root degree converge in distribution or does it converge to a constant? And so essentially for things like the cutoff preferential attachment model, the competition induced preferential attachment model, so I still haven't told you what this is, but I'll tell you. For these two things and the sublinear preferential attachment model, for all these things they converge to a constant, whereas for these other models, there's too much information, but anyway they converge to in distribution to some random variable. Okay. So you can get somehow very quickly you can get lots of results both about the root and the maximal degree. Okay, sorry. So any questions regarding, this is just the root and maximal degree. Okay, so now another thing that you might be interested in is the height of the tree. So by time n, there's some person who's furthest from the root. What is the height of the tree at this time? So again, using these stochastic process type ideas, you also very quickly, so this is basically the entire rigorous proof of what the height of all these models should scale as. So you very quickly get what the height should be. So what is the basic argument? We use Kingman's result. So what Kingman, in a very nice large deviations type result, what he proved is the following. So you have one of these continuous time branching processes, and you ask, what is the first time for me to observe a person in generation k? So that means a person at distance k from the root. What is the amount of time I have to wait before I see a person in generation k? Then what he proved is the following. It basically scales linearly in time. So the amount of time I have to wait for such an individual to be born divided by k, this converges almost surely to some particular constant which depends on the model. And there's an explicit constant. It's difficult to compute or get an exact formula for this, but there is an explicit description of what this constant should be depending on the model. So how do you use this for the height? So for your tree n, you construct your tree n by time tn, and you know that since by definition in your tree there is somebody at height hn. So hn is the height of the tree. So there is already somebody who's been born who is at distance hn from the root. The time for the birth of a person in generation hn is less than or equal to tn, the time for you to construct your whole tree using this continuous time ideas. But this is less than or equal to, there's nobody of height hn plus 1. Okay. So then just divide by hn, and use this result and the fact that you know exactly how this tn scales to conclude that hn by log n converges in probability to some constant which depends on the model. So model by model you get exactly what the height should scale as. Okay, so this is height, but then you might be interested in percolation. So you have your network and then you're going to delete edges with probability p and retain them with probability 1 minus p. So how, so can you say something? So the thing is, these kind of methods actually tell you exactly how the structure of the percolation component about the root should look like. So if these methods also tell you, you look at the percolation component at the root. If I ask what is the asymptotic degree distribution of this, then I can exactly tell you what the asymptotic degree distribution is, not just what the size is. So how does one go about doing this? So remember I was given a point process, so given any model, I constructed this point process, and then I constructed a continuous time branching process and I analyzed this. Corresponding to a point process, you can define a pruned point process. So what is this? I basically keep each of these points with probability p and remove them with probability 1 minus p. So just marking them. So I keep some of these points, I remove other points. So each point I keep with probability p and remove with probability 1 minus p. So this gives me another point process, just a pruned point process. So you look at our old branching process driven by this old point process p, and it has this computable Malthusian rate of growth lambda. Similarly, you have this you can define a branching process which is driven by this pruned point process, the same story. Each person produces at this rate, at this point process instead of the old p. And you can compute a corresponding Malthusian rate of growth. Okay. So the general theorem is, assuming some technical conditions, if you look at the size of the percolation component attached to the root and divide by, divide by lambda p divided by lambda, so the ratio of these Malthusian rates of growth, this converges in probability to some random variable which is strictly greater than 0. So what is the basic conceptual idea? Sure.
Inside what?
So Cn is the percolation component of the root. Inside the whole tree.
What is n in Cn?
The number of
And the tree n. Right.
Do you do percolation on the whole infinite tree or on Tn?
No, just Tn.
Yeah.
Right, just Tn. Okay. So the basic conceptual idea is the root component essentially looks like this, this pruned percolation branching process driven by this pruned percolation process. So if you look at the size of the percolation component at the root, that is basically looks like this branching process observed up to time tn. Now you know that tn scales as 1 by lambda log n. Okay. So you know that the time, so tn looks like 1 by lambda log n, whereas this quantity fpt, that grows as e to the lambda pt. So if you just put these two together, you basically get what the size of the component should look like. And you get some interesting, easily computable results. So for example, if you look at the Barabasi-Albert model, that scales as n to the 1 plus p over 2. So for any p positive, it always has, the root component is always of size greater than square root n. And if you look at the percolation component for this linear model, so k plus 1 plus a, then you can compute explicitly what the size of the root component should look like. And the point is, can you actually show that, the open problem, which probably will boil down to some sort of large deviation computation, is this the scaling also of the giant component? So you look at the largest component in one of these trees. So my feeling is they still scale in the same manner. So n to the 1 plus p by 2, and you have similar results. So can you prove something like this? Okay. So this was global results. What can you say about the global parts of the tree? So now I'll tell you what you can say about local asymptotics, exactly what the structure of the tree looks like locally. Okay. So what am I going to do? So for any given model, I'm going to tell you a construction of an infinite tree, but which is locally finite and has one end. So there's just one path which goes off to infinity. And the point is, if you take any model and you sample, so you take a uniform node at random, pick a uniform node in your network at time n, then the structure of the neighborhood of that node, the uniformly sampled node, somehow looks like the neighborhood of the root of this appropriately constructed single infinite tree for reasonably large n. So that's the basic point. Okay, so this is stuff which has been developed by Jaggers and Nerman and so on, and Aldous, in some sense, he made it more readable. So along with many other very nice results. So the basic idea is the following. So you have your tree at time, so this should be ftn, but anyway, so given your tree at time n, suppose you sample an individual uniformly at random, and if you ask what is the chance that my uniformly sampled individual has age greater than 10 units. So he was born at some time. What is the chance that his age is greater than 10 units? Because he was uniformly sampled, the chance that his age was greater than 10 units is the number of people who were born before time, 10 units before the time that you sampled, t, divided by the total number of people at this time. Okay. Now I told you asymptotically, essentially, this quantity is w times e to the lambda t minus 10. So they grow explosively at this rate, divided by w e to the lambda t, where this w is the same. So this is basically the asymptotic growth of these branching processes. So this is e to the t 10 times lambda. So this is the probability that an exponential random variable is greater than 10. So the basic point is the following. You pick a person uniformly at random, then his age is approximately exponential with the rate lambda, where lambda is this Malthusian rate of growth. So, this is the basic heuristics for the following construction. Okay, so again, so this is slightly technical, but then it gives you a lot of information about random matrices, spectra, and so on. So you do have to get into it. So what is the construction? So this is an infinite tree which depends on 3 parameters. It depends on alpha. So alpha is usually this Malthusian rate of growth for any model. It depends on a measure mu. Mu is some measure on the positive real line. And it depends on this point process p. For any attractiveness function, this point process. So it depends on 3 parameters. And how are you going to construct it? So you're going to first generate random variables. So you generate x naught, which has the distribution exponential with rate alpha. And for I greater than or equal to 1, so the first random variable x0 has an exponential distribution with rate alpha. And all the other random variables are IID, independent of x naught, with this distribution mu. And then you look at this partial sums, Sn, which is the sum from 0 to n, xi. Okay, now once you're given these partial sums, so this is a random walk with the initial start as an exponential random variable, the rest have this measure mu as the distribution. Once you're given these random variables, you're basically going to paste together an infinite number of continuous time branching processes, all of which you observe for these amounts of time. So what do you do? Okay, this is not very clear, but the point is the following. So once you have this random walk, S0, S1, S2, and so on, what you're going to do is you're going to paste an infinite number of continuous time branching processes. So script S0, so this is a continuous time branching process with this rate, with this point process P, which you observe only for time S0. This is another continuous time branching process, independent. So all of these are independent, which you observe for time S1. This you observe for time S2. So they are all independent, but you observe them for only S0, S1, S2, and so on amount of time. And there is a minor quibble about there's some. Okay, oops, sorry. Somehow for these guys, this person. You have a continuous time branching process, but you have to condition this person to have a child at this time. You have to condition this person to have a child at this time, and so on. So there is a minor quibble some fudge factor there, but essentially you're observing these countable number of continuous time branching processes for some random amounts of time, each of them. Okay, so this is an infinite construction of a tree. And suppose you're only interested in this infinite tree up to 4 ancestors away from the root. So this is the root, 0, and then you have this entire infinite path. So suppose you're only interested in 4 ancestors away from the root, then basic notation is this is the okay. So the last line, this is basically the infinite tree which you truncate up to distance k from the root. Distance meaning the number of ancestors of the root. You truncate it. So this, okay. So what is the point of all this? So fringe and extended fringe, they've been used a lot in computer science. So there's a structure theory for finite trees. So suppose you're given a finite rooted tree, and so you're given a finite rooted tree, so you have a particular root, and you're also given a vertex v. So there are 2 things you're given. Then you can construct the fringe and the extended fringe. So what is this? So the fringe subtree rooted at v is basically all those nodes for which the path from the root has to pass through this particular vertex. And the path from the root to this vertex v, so this is the particular root, so the path is v0, v1, v2. This is the path from this particular vertex to the root. And the extended fringe are all these subtrees. So this subtree consists of all those nodes for which the path from the root has to pass through this particular vertex, and so on. So this is...
What context is this used in computer science?
I'm not very sure. Well, in algorithms. But yeah, it exists in computer science, but I'm not very sure. So essentially, I think to analyze how good are search algorithms on trees, they use this notation for fringe and extended fringe. Okay, but yeah, not very sure why they use it. Okay, so anyway, so given a finite tree and given a vertex v, you can define this fringe and this extended fringe for this particular vertex v. Okay, so this is what I told you. And again, similar to the previous concept, you can define, suppose you're interested in only, for a particular vertex v, you're only interested in the structure up to a distance k on the path to the root, then you can define the truncated fringe. Okay, so there's a lot of notation, etc. But so what is the point of all this? So you say that a sequence of random trees, so you're given a sequence of random trees which is increasing. So you say that this converges in fringe sense if the empirical proportions converge. So what does that mean? Sorry. So what does that mean? So you look at, so fix a particular k. So k is how the distance from a vertex that you're interested in. So fix a particular k, and you look at, so you count the number of vertices. Okay, so also fix trees t1, t2 up to tk. So these are just trees. And you ask, what are the number of vertices v in your whole tree such that the structure of the neighborhood around that vertex up to distance k looks like this tree. So you count this, and so you look at the proportion of this. So this is the empirical proportion. And you say that this random tree converges in fringe sense to an infinite sin tree. If this converges for every fixed k and every fixed t1 up to tk, this converges in this probability fringe sense. So this converges in probability to the corresponding value for your infinite sin tree. So this is an idea of convergence of finite trees to an infinite tree locally. So this is one particular idea developed by Aldous. Well, so developed by Jaggers and Nerman, but actually put in a readable form by Aldous. And okay, so the notation is tau n converges in probability fringe sense. This is just a notation. So
how it relates to what
no, I'm not very sure.
It's equivalent. It's equivalent, but it's more special, and it was earlier.
Well, in what way is it more special?
Because he only considered it for trees, and they were.
Oh, okay, good.
This is for trees, and you also need to remember in which direction the root is.
Right.
Uh-huh. But it is a very similar. It's the same notion in the cases in which it applies here. Okay.
And does it now, the original definition was only for 180 degrees. So So I was thinking
They were interested in bounded degree because they had a theorem about bounded degree.
and then there was bounded average degree by
The notion of convergence is the same, and you can define it even without the bounded degrees.
right, but then who was this who did this? Did the bounded average.
Ruts. Yeah, but
So
the
this
point was
was
not
originally
the
done
difference,
for
right?
bounded average degree.
But the definition worked. I mean, it's a natural definition. It works for bounded average degree also.
Okay, so it is like, because Benjamin Schramm is a very natural notion
Right.
of a local convergence for these preferential
This is the same.
attachments.
This is the same notion. It was earlier,
Just for
but
trees.
for trees.
Okay, so what Jaggers and Nerman proved, this general branching process.
You know that we have this. I know, but no one talked about it.
Right, I mean weak distributional limits
Yeah.
for our local weak
So no
convergence.
one talked about it at the conference, but you learned about this.
Right, yeah,
We
yeah.
have convergence in general to the Benjamin-Schramm convergence.
Right. But the point is, for all the models, you can explicitly compute exactly what alpha, mu, and p is. So I can tell you an exact construction of your local neighborhood.
So can be.
Okay.
Yeah.
Right.
And I think no one talked about that, but anyway, yeah.
Right. Okay, so alpha is this Malthusian rate of growth, and mu is what is called the sin measure. So this sin measure, it's difficult. There's a difficult formula to compute in various models, but it is in many of the models it's explicitly computable. Again, a lot of formulas, but the basic point of the slide is you can actually compute what the sin measure is. This sin measure was you have this random walk. So you can explicitly compute for various models. So for example, for the Barabasi-Albert model, it's just the exponential random variable with rate 1. For the linear preferential attachment model, it's just a mixture of exponentials with different rates, exponential gamma minus 1, exponential gamma. For the competition induced preferential attachment and for the cutoff models, you can also compute. There are some formulas, but anyway. So the point is you can actually compute all the quantities that you require. Okay, so I won't get into too much detail, but just as an example, so this has been completely solved by Jennifer, Christian, Reiser, D'Souza, and Noam Berger. But just how do you use these results? Sorry?
And Bobby.
Oh, okay. Okay. So how do you use the results that I told you to do computations in this particular model? So I'll first tell you what the particular model is. There's a complete story as to how this model arises because of two competing forces. There's a spatial aspect and so on, but they have a nice computation which shows that it boils down to a preferential attachment scheme. So the Markov description is the following. So there are two types of nodes. So you start off with one node which is fertile. And then there are two types of nodes. At any given stage, there are two types of nodes, fertile nodes and infertile nodes. And only fertile nodes reproduce at the next stage, meaning when a new node comes in, it's immediately put in as an infertile node, and it can attach itself to only fertile nodes. So at time t equal to 1, you start with one fertile node. And at each time, so for any given time, a new node is born, it's designated infertile, and it is attached to a fertile node with probability proportional to. So you take a fertile node, you look at basically the degree of that node, but cut it off at some a. So a is a parameter of your entire process. And they've analyzed more general models, but this is the base case. Now, so you attach a new node, and after you attach this infertile node, so for a particular vertex, a fertile vertex, the mother of this new node, if the number of infertile nodes is equal to a, so it has too many infertile nodes, then you make one of those nodes as a fertile. So choose one of them uniformly at random and make it a fertile node. So this is a Markov description of an attachment procedure. So, okay. So if you think a little and go through some details, essentially the model, when you're just interested in the tree of fertile nodes, looks like the following. So you have the point process corresponding to this continuous time construction is the following. So S1 is the sum of some exponential random variables with some particular rate. And S1 is the sum of random variables, sum from 1 to a, yi over I, where yi are exponential random variables. And Si plus 1, so after you know the first point of your point process, Si plus 1 is Si plus yi plus 1 divided by a. So this a remains fixed after that. So if you look at Tn, this is the amount of time it takes for the number, so this should be fertile, but the number of fertile nodes, so this point process represents the construction of your tree consisting of only fertile nodes. So if you look at the amount of time, you stop this process when this branching process is n over a, then this branching process has the same distribution as this subtree of fertile nodes. So when you do the global analysis, so this Malthusian rate of growth, theta a is equal to 1, you can prove very easily that the degree divided by log n converges in probability to a, or 1 over a, so there might be a typo here. And then the height divided by log n converges to some model dependent constant. So this is what somehow Reiser said that you don't know the global characteristics of this tree. Anyway, so that's, yeah. So the global characteristics perhaps are a bit difficult. So anyway, so this is what the global characteristics are. And locally, it converges to one of these infinite trees, where the measure mu is equal to this particular weird-looking quantity.
What was degree of rho? Can you go back?
Degree of the root. Degree rho is the degree of the root. So the root degree divided by log n converges to, I think it should probably be 1 over a or a. And the height converges to some constant. Right. Okay. And now, so this is stuff which has already been proved. I'm just telling you how you do the computations using this entire story. So this convergence in probability fringe sense, this immediately tells you, okay, so first, so if you look at the number of nodes with degree k, that converges in probability to a constant, this pk. So what is this pk? Pk is, this constant pk is the degree of, in this infinite tree construction, it's the degree of this root. What is its degree? That is a particular random variable. So the degree distribution converges to that particular cause. So the probability that this root has degree k, these random quantities, the empirical proportion of nodes with degree k converges to this constant pk. Okay. Okay, now what is the degree of the root? The degree of the root, because of this entire story of construction, this has the same distribution as your point process observed up to time, an exponential with rate theta a random exponential amount of time. Okay, so this is, you can just repeat these computations for any of the models. So the probability that your root has degree greater than k, so the probability that this quantity is greater than or equal to k, this is the chance that at least at least k children, so the time for the birth of k children is less than this exponential amount of time. And this is just a formula for the exponential random variable. And if you actually go through the computations, you just derive what they had, the degree distribution. So this converges in probability to these constants.
So the only mistake here is that there should be a K, B, B, C.
K, right. Right. Okay, so this is good, but you can do more advanced computations. So you might be interested, so you have these random trees, and you look at the adjacency matrix. So these trees are graphs. You look at the adjacency matrix. This is a symmetric matrix, and you might be interested in the spectral distribution. So you have the distribution function, which is you look at each of you look at this adjacency matrix, look at its eigenvalues, and you look at the delta measures, the empirical distribution of these spectra. And the question is, can we say anything about this? Can we say anything about the maximal eigenvalue? So it seems that perhaps some of this you can say something, but it's still like work in progress. So what is the basic conceptual idea behind why the syn tree, etc., all these complicated constructions, why any of these things can help us? So the typical method to analyze the eigenvalues for random symmetric matrices, or probably the only method, is the following. So it's basically the method of moments. So you look at the symmetric matrix, multiply it k times. You look at the trace of this matrix, 1 over n of this. So 1 by n trace of, you show that 1 by n trace of ak, which is basically the kth moment of these eigenvalues, you show that this quantity converges to some constant qk. For each k, it converges to some constant in probability. And then show that these constants qk, they uniquely determine a measure. So this is the usual way of showing showing that the empirical distribution of the spectra converges to something. So in this context, what is the trace of ak? So trace of ak, you just multiply, this is just notation for the diagonal elements. So what is the diagonal element? So aiik, so in ak, aii, the ith diagonal element, is the number of paths of length k starting at node I and ending at node I. Okay, so you can, in theory you can compute for given any model, you can compute what are the expected number of paths starting from a node, the expected number of paths of length k starting from this node and returning to this node. So with this entire SYN tree you can compute it. And what this entire story suggests is qk is just this particular quantity, the expected number of paths for the root of length k starting from the root and ending at the root for any given model. So the challenge is to actually prove it. And we are vaguely sure that it holds in many cases such as this cutoff model, competition induced preferential attachment and so on. But it does not, this kind of method does not work for the usual preferential attachment model, Barabasi Albert type model, and for that you'll actually need new techniques. So that's why somehow it is interesting. Okay, so almost out of time. So let me quickly tell you so how much time do I have? Sorry. In theory I know 5, but
what?
No, in theory I know it's up to 5, but in practice.
No, but it's
right.
not.
Right.
Okay, so maybe 5 or 10 minutes. I don't know.
Okay, sure. Okay.
We just give an hour and a half because sometimes we totally attack the speaker and we wanted to have this full hour. But I don't think we totally attacked.
Right, not yet. Okay, so you can.
Reserve the right.
Right, absolutely. We'll do that between 5 and 6 when we talk.
Okay. Okay, so up to now I told you about these preferential attachment trees, but these methods also very quickly in 1 or 2 lines they also tell you a lot of information about preferential attachment networks. So maybe I should just tell you the result, which is somehow I think not derivable using usual techniques. So I'll again remind you about the model. So at time k, a new node k comes in with wk out edges, and it tries to attach itself one by one preferentially to the network. This is the basic attachment scheme. Okay, and the point, or one of the key ideas for analyzing these networks is there's a correspondence between the tree and the network. So this is always where f of k is k plus 1, not for any of the other models, but just f of the attractiveness function is proportional to the present degree. So there's a correspondence between the tree and the network, which is used a lot. So what is it? So suppose you want to construct a network like this on n nodes. What you can do is the following. First, generate these out degrees, wi. Look at the partial sums. So Sn, this is the sum from 1 to n wi, and in general sum from 1 to I wj, si. So you look at the partial sums. First, construct the usual preferential attachment network on Sn number of nodes. So many number of nodes. You construct your tree. And then you basically start coalescing consecutive nodes. So you have this partial sum, si. So start with s not equal to 0. Merge nodes from, si minus 1 plus 1 to si. Merge all these nodes. There are wi such nodes. And you call this node I. And the network that you get corresponds to a preferential attachment network. Okay. So this is this connection between networks and trees. Okay, so this kind of description is somehow not known. So suppose your out degree, the expected out degree is less than infinity. So this particular description is new, but you can show that if you sample a random node, then it converges in distribution to some particular random variable. So that characterization is new, but what has been proved by Remco, van der Hofstad et al. Is that using recursions is that the same. So they explicitly derived what is the probability that this random variable is equal to k. So it's equal to something like this, and you can show that the number of nodes with degree k divided by n converges to something. So you have convergence of the degree distribution, but so using recursion somehow perhaps you can stop up to here, but very simply using this entire story about continuous time branching processes, if you assume that the random variables have exponential tails, it's very simple to show that the maximal degree will be of order square root n. Okay, so this is a finite mean case, which is known in some sense and not very new. But what is interesting, at least at a mathematical level, perhaps not that much as a modeling level, is the following.
So I'm sorry. What,
sure.
The mean of what? Finite mean, infinite mean?
Right. So the finite mean of so each node comes in with a random number of out edges. So assume that the number of out edges that you have, this is a random variable. Assume that this expectation of this random variable is less than infinity. That's a good question. So if you assume this, then you can prove something. But okay, so now suppose you assume that each node comes in and it has a random number of out edges, but these out edges don't have a finite mean. So suppose you assume something of the following. So x, so they have a heavy tail distribution. So x to the alpha times the probability that w is greater than x, the out degree distribution. This converges to c for some c greater than 0. So assume that they look something like this. So it's well known in classical probability theory that these random variables belong to the domain of attraction of an alpha stable subordinator. So what does that mean? So this should be SNT, but anyway, so if you look at these partial sums, rescale by n to the 1 by alpha, so similar to random walk converging to Brownian motion, these quantities converge in distribution to something called a Levy process, so some process xt, which has left limits and is right continuous. So it's a stochastic process on 0, 1, which is always increasing and has left limits and is right continuous. So it's a stochastic process. Okay, so now I'll just go through one or two definitions. So now suppose let u be a uniform number between 0 and 1, and suppose you have this xt, this is the stochastic process. So construct this random variable, so z alpha, so this is equal to something, so negative half 1 by alpha log of this u plus log of, so you look at this stochastic process, pick this uniform number which you sampled. So both of these random variables are this stochastic process and this u are independent. But anyway, so look at xu divided by x1, the terminal value x1, and you look at xu, some uniform point between 0 and 1. And you have the same u over here, and you form this random variable. So for each particular alpha, you can define this random variable. So then what you can show is, if you look at you pick a node at random in your network, you ask, okay, what is the degree of this random node? This converges in distribution to the sum from 1 to w. Okay, so ni's are Yule processes, independent Yule processes, independent of everything else. Z alpha you have constructed like this. So you sum up w Yule processes and observe each of them for the same amount of time, z alpha. So this is a particular integer valued random variable, so weird construction. So the degree of a randomly sampled node converges in distribution to this particular quantity. A long description, but the proof itself is simple, and it's not clear if you can derive something like this using other methods. Okay, and for this particular case, you can show much more. So if you look at the root, the first vertex that started this whole process, then what you can show is that the degree of the root divided by n to the 1 by 2 alpha, this converges in distribution to some random variable. Whereas the maximal degree, just using extrema of independent random variables, that actually scales as n to the 1 by alpha. So so in this case, somehow there is a big difference between the root degree and the maximal degree. Okay.
So,
sure.
So you're doing it. Okay, so maybe like brief on
Right, yeah, no, I'm going to skip through a lot of
you can
this.
tell us about the fitness stuff.
Right. So, these are half-baked, I don't know if they seem doable, but I'm not sure. So it's just some open problems. So I told you how the structure of the root component, percolation component for the root looks like. It scales as some Malthusian lambda p divided by lambda. So in some sense it looks like the maximal, what is of interest to the giant component, what is the biggest percolation component. So that also should somehow scale in the same way, and that should also converge in distribution to some random variable WP. So this is an open problem which I think should be doable. But what is of slightly more interest, which I have no idea how to do is, and this is known, but the question is, can you get a nice simple proof, because all the proofs seem somehow complicated, is the following. So you look at the preferential attachment network model, where each node comes in with let's say 10, m equals 10 out edges, and then attaches itself. So you're looking at the network. Now if it was not a network, if it was a tree, what this result says is there's at least one component of size n to the 1 plus p over 2. So for any p, there's always a component of size greater than square root n, much larger than square root n. So can you somehow bootstrap this information to conclude that for any p, whatever p be, this is known, this is results at least proved by Barabasi and Riordan, right, among presumably other people, but this is known that, so it is known for the preferential attachment model, that network model, that for any p there's always a giant component. That is, there's always a component of size n. Although the constant could be small, but there's always a component of size n. So can you somehow easily from this bootstrap your way to some much more powerful result using this connection between the tree and the network? And again, using this height ideas, and if perhaps using Kingman's ideas, the paper itself is very nice, using martingales and large deviations, a very nice paper. Again, for the preferential attachment network, so somehow the geometry changes to a large extent in the sense that the diameter of the network scales as log n divided by log n. So can you somehow show that can you get a simple proof for this particular result?
No, that is again no.
That is, sorry?
That Bobash and Reardon, of course.
Right.
That was their
No. I know that this is known. No, the question is, right, because I have not been able to understand the proof, but yeah, it's definitely known.
Well, I think you can probably do that with like our polyurn more easily than their, we talked about that. The polyurn, you can do it much more easily than their...
Getting the diameter?
What do they call their...
The linear chord diagram, LCD or something.
Yeah, the LCD model.
Right. So anyway, so the question is, right, so this is known. Otherwise I would not be, convergence probably, so can you show something like this? And okay, so there's some more conjectures in terms of the maximal degree. Does the degree converge in distribution or so I know that I can get bounds on, so I can say statements like the probability that the maximal degree will be larger than some constant is less than epsilon for any given epsilon, and for some scaling factor Wn, but can you get actual distributional or constant convergence?
I think, you're going to be here the whole week, so I think...
Right, I'm done, basically. So order, not so nice cases, so let me just mention that somehow there are mathematically very interesting models which don't fall into this entire setup in the sense that if you use this continuous time construction, then they explode in finite time. So, all this doesn't exactly apply to them. Like the superlinear preferential attachment model, k plus 1 to the alpha, or various cases of the random fitness model, where, so the nice...
The fact that this continuous time model exploded in finite time is actually one of sort of the key ingredients in this guy's proof. So
right.
And there has been this mapping to having sort of this independent processes in continuous time. Right. And one of them explodes sort of in finite time.
Okay.
And all other ones are finite.
Are finite.
That's how you prove the monopoly.
Right.
I don't quite know what you mean by it doesn't apply. It was applied.
No, I mean...
Standard result has been proven by massive...
Sure, no, I'm just saying this entire sin tree construction, this Jaggers-Nerman machinery doesn't apply to this setup. Oh. You're right. Right. No, I know the techniques that are used are often these exponential, rate 1 techniques, like Spencer and Oliveira. Their methods use this exponential rate 1 construction.
What doesn't apply is the proof of the local content of the iris of intermediate transformation.
Right, exactly. At least, the way that I formulated it. So that does not apply. Okay, so anyway, I had the conclusion at the beginning, so that's it.